now we move to the second contributed paper of the conference. So this paper is from Lucas Gautheron.
Yeah.
Okay. So yeah, double affiliation, both Germany and France, and he's presenting a paper on a dialogue between philosophy of science and computational studies of science illuminates the crisis of fundamental physics. So I think it's very good talk to conclude this day of the workshop, because it brings together lots of the themes that we saw today. So please, Lucas, the floor is yours.
So thank you very much for the opportunity to present and also the great talks. Okay, so I just start right away. It's actually okay. All right. So the questions that I will address today are sort of framed into traditional like philosophy of science literature, but deep down, I'm really interested in studying science using cultural evolutionary perspectives and computational methods. So, for instance, themes I'm interested in are collective intelligence, collective action, collective adaptation, and how we study that using sort of scientist behavior as a playground for these studies. But my PhD focuses on high-energy physics, which I think, with respect to these issues, is very interesting because it has a very complex division of labor, and also, as I will try to show, is in a peculiar situation of crisis, which exacerbates issues of coordination and also of adaptation. So first, I have to give some context about the situation in fundamental physics. So historically, high-energy physics have achieved progress by building larger and larger particle colliders, right? And so this logic has culminated with the Large Hadron Collider, which includes about 10,000 collaborators, give or take. And for instance, you can see the tunnel of this particle accelerator, which is 27 kilometers long. And so just to give you an idea of the scale of this experiment, so this is one of the experiments at the LHC, and so you can see, maybe you can see it, maybe not a human in comparison. All right, so what we do in these experiments is that we accelerate protons and we collide them against each other, and this produces many particles, and we measure them, we analyze them, and then we gather some knowledge about the phenomena involved. So why do we bother making such large experiments to begin with? So the reason is that the larger experiment accelerators you build, the higher energies you reach, and the higher energies you reach, the more phenomena you discover. So for instance, if you reach this energy here, the QCD scale, as we call it, you start to be able to probe the inner structure of the protons. And if you go a bit higher up, you start to be able to probe what we call the electroweak scale. And so then you can discover the Higgs boson, for instance, which is the last fundamental particle that was discovered. And so today we are about here with the Large Hadron Collider, right? But in fact, there are other energy scales that you are interested in. So for instance, if you are interested in achieving unification of fundamental forces, you would like to study what we call the grand unification scale or the Planck scale. The issue is that it's actually impossible to probe these scales with particle colliders, because due to technological limits, that's about as far as we can go. So then it's quite unclear whether we can actually get knowledge of these high energy scales by exploring the electroweak scale, for instance, at the LHC, as we do, or conversely, that theorizing about unification can bring information useful for guiding experiments at the electroweak scale. And so, in fact, we had some theories that told us that maybe we can find some hints at the Large Hadron Collider that our efforts to unify forces of nature are correct. And so, unfortunately, these hints have not materialized. So now it seems like we cannot really have these exchanges between high energy scales and the electroweak sector. And so this is why the field is in some sort of situation of crisis. So first, I will show that this raises this exacerbates the disunity of high-energy physics. So indeed, roughly speaking, you can divide theory in high-energy physics in two sort of broader approaches. One of them is phenomenology, which is really committed to modeling interactions between particles as they can be observed in experiments such as particle colliders. But you also have something that you might call high theory, which is committed to achieving unification of forces, understanding quantum gravity, understanding the ontology of space-time, etc. And what's happened is that historically, so these two things have really been able to achieve progress hand in hand. But since the Large Hadron Collider, the possibility of achieving progress and hand in hand between these two approaches is now much less plausible. So I think one way to make sense of this situation is to appeal to Peter Gallison's account of the disunity of physics. So according to Peter Gallison, physics is split into subcultures, which basically are distinct subcommunities with their own sort of technical jargon, which nonetheless can exchange sometimes knowledge within what he calls trading zones, okay? And this is how physics acquires its robustness in spite of the fact it's extremely diverse. So I think this account kind of invites us to look in, to regard theory and phenomenology as subcultures, and this is where I think we can sort of include quantitative methods into our approach. So indeed, so phenomenology and theory, they are actually categories of the literature, which is convenient, which makes it very easy to analyze them quantitatively. And so if we want to see to what extent those things can indeed be seen as subcultures, then first we can verify that they have a social component. There's a social divide between those two things. And so I don't have time to go over this, but this is what we show. We find that basically you find, so each red dot is a physicist, right? And so you have one cluster around phenomenology, one cluster around theory. And even though you have some people in between, you do find some evidence of communities tied to these categories. But then you can also explore the linguistic divide, which is so important to Gallison between these two things. And so for that, you can use like prehistoric method of natural language processing. So you can actually train a model to predict whether an abstract belongs to either of these categories. And you find out that even a basic model can actually do it quite well. And then you can use the weights that the model learned to sort of extract which keywords are most representative of each category. And so then you find some interesting things. For instance, you find that there's some sort of ontological divergence between those two things, with phenomenology putting more emphasis on entities such as particles, and theory putting more emphasis on space-time constructs. Also, you find references to experiments in phenomenology, which are completely absent from theory. And finally, in phenomenology, there's a lot of appeal to often approximate models, whereas in theory, there's more emphasis on idealized models. Okay, good. Something else that is valuable in Gallison's approach is that he suggests that subcultures can exchange knowledge despite of the divergences and coordinate their progress as long as they find some tradable goods or concepts, okay? And so this raises the question of what concepts have sustained fruitful trades between theory and phenomenology for the years, for instance, 2000 to 2020, because the LHC started in 2010, so we might want to know what happened before and after. So for that, we can notice that the citation network is in fact a proxy for the trading zone, since indeed citations across subcultures signal successful exchanges of knowledge. And so then we do that, and we look at, for instance, citations of phenomenological work by theoretical work. And so to the left, we can look at the concepts that have declined the most abruptly inside of the trading zone over this time period. And to the right, the concepts that have risen faster. And so again, I don't have time to go into the details of this, but what we found is that the concept declining most rapidly are mostly related to the electric scale that we explore at the LHC, whereas those that are rising are mostly related to astrophysical input. Okay. And so we find the same sort of patterns if we look at trades the other way. Okay. So to summarize this part, so Gallison proposed an account of the disunity of physics as being divided in subcultures that mean namely distinct communities with their own language, exchanging via trading zones. And I think his account invites us to regard high-energy physics theory and phenomenology as autonomous subcultures, and then operationalizing Gallison's concept into quantitative constructs enlightens the divide between these two subcultures, but also reveals the transformations of their trading zone over the last 2 decades. And finally, this reveals a shift to the cosmos and away from collider and electric scale physics in the trading zone. So it's somewhat valuable. Okay, so I didn't have time to explain much about this work, but if you're interested in reading about it, you can find it in this paper. Okay, so now we'll discuss another issue that is raised by this context, which is an adaptation problem. But I will use an opposite approach. So instead of starting from some sort of philosophical account and trying to see how we can implement it quantitatively, I will start from a computational model from the optimization literature, so nothing to do with philosophy or science. And I will try to see that it can maybe, well, you will be the judge of that, but it can maybe suggest philosophical insights, okay? So Parallel to the Large Hadron Collider, which started in 2010, alternative opportunities have emerged. So, for instance, we had new direct searches for dark matter, gravitational wave detector, we had new probes of the early universe, etc. So, in other words, what happened is that the landscape of research opportunities has been reshaped. So one question that we might ask, which is very empirical, is how have scientists adapted to these transformations in the landscape of opportunities? And so this question, in fact, can be addressed quantitatively. And the argument that I will try to make is that the patterns of adaptation that we observe within the community can be made sense of in terms of optimal transport, which is a mathematical framework which deals with the optimal allocation of resources, which then in turn provides general insight about scientific exploration. Okay, so for this project, so I clustered the energy physics literature into 16 research areas using an embedding topic model trained on about 200,000 abstracts. And so then, based on that, I extracted the research portfolio of a bit more than 2,000 physicists before and asked. So as shown here, the start of the LHC and after the start of the LHC. So on this diagram, so each color represents a different research area recovered by the topic model. And so then once we do that, we can actually look into how efforts were reallocated. So I will show you that. Okay, so I don't have time to go over the technical methods, but you may ask if you're interested. So in fact, the initial motivation for doing this was to try to understand which factors enhance adaptability, thank you, and among this cohort of physicists. And so in particular, I wanted to know if the diversity of intellectual and social capital was a positive factor of adaptability, and it seems to be the case. And interestingly, conversely, social power seems to be negatively associated with change. But again, so this is not the focus of my presentation today, but if you're interested, you can find more about this in this manuscript on arXiv. Okay. So this is what we get. So if you aggregate all the research portfolio of all the physicists of the cohort, and you aggregate transfers of attention from one distribution to the early distribution to the left, to the late distribution to the right, so you find this. Okay, so again, each color is a different research area. And so this is a bit messy, it's hard to interpret that, but we can still see some distinct patterns. So for instance, we can see a collapse in neutrino and flavor physics research, which is in part explained by a refocus on dark matter. And in fact, we see that the dark matter topic has doubled in size as a result of migrations away from neutrino physics, but also the electrolyte sector, which again is what is being explored at the Large Hadron Collider. And you can also see some significant changes in string theory and supergravity with a refocus on holographic dualities, which we mentioned a bit with the Dasena paper. Okay, so now what I'd like to do is to try to provide a broad level characterization of this. And so because philosophers are usually interested in narratives about science, so let's try to provide a story of this overall structure, okay? So for that, I will appeal to optimal transport. What is optimal transport to begin with? So it's a mathematical framework that was introduced by French mathematician Gaspard Monge in 1781. And the question that he asked then was, what is the optimal way of displacing piles of sand in order to fill a certain amount of holes? Okay, so, and he didn't ask that in the vacuum, he asked that in a military context, okay? Okay. So for instance, here, the blue dots are piles of sand, and the red dots are holes, and what is the way to move around the sand in a way that minimizes your effort? This was the question. And so this is the solution to this particular problem. You won't find any better solution. This is the optimum. Okay, so now you probably wonder, why am I discussing these things, and what does it have to do with science? Well, actually, optimal transport is more general than that. So the underlying question is how to efficiently displace or allocate resources, whether it's matter, goods, or people, to specific locations or tasks. And so this was introduced in a military context by Monge, but later the framework was refined by Leonid Kantorovich in the context of economic planning. So you can see the generality of this framework. Okay, so you have basically two approaches, two sort of ways to frame optimal transport problem. One of them is transportation problem, you move stuff, but one of them is matching problem. So for instance, you assign an individual to a firm in economics, but more generally to any task. Okay. So optimal transport problems are defined by a cost matrix, which specifies how costly it is to displace something from X to Y. So typically in transportation problems, so for instance, books being transported from warehouses to customers, the cost matrix is a distance matrix, okay? The distance between each warehouse and each customer. So here, for instance, the blue dots would be Amazon warehouses, and the red dots would be us ordering online and putting bookshops out of business. And then the cost matrix, you can see here, the distance matrix is represented by different shades of red, which represent whether it's different warehouses or very far or very close to each customer. And then, given this cost matrix, you want to decide what is the optimal way to move around the items. And so this is what optimal transport does. It provides you the most efficient assignments. Inverse optimal transport, on the other hand, aims to recover the underlying cost matrix given the assignment. So you start from the assignment, you know how stuff has been moved, and you try to infer back what could have been the underlying cost matrix. So this is the inverse problem. So now I'd like to go back to physics, and my suggestion is to look into that as an optimal transport problem. So indeed, you can see here that we start from an initial distribution of research efforts, and we have changes in the landscape of opportunities. So we want to sort of reshape, to reallocate research efforts, right? But we want to do that in an efficient way. For instance, you want to do more dark matter research, but well, then it means some physicists will have to make the switch, but who should make it, right? So that's, and you want to do that efficiently. So in our case, we know how the cohort has adapted. So we have recovered the transfers. So basically what we could do is sort of solve the inverse optimal transport problem and try to recover what is the underlying cost matrix that is minimized by scientists' adaptive behavior, right? And so for that, we use this method, which is probabilistic inverse optimal transport, and we can recover the cost matrix. So again, it's kind of maybe unclear at first sight. So basically what this shows is the cost of migrating from each horizontal research area to each vertical research area, which you recover based on the observed scientist behavior. Okay, so we recover that, but we'd like to have, again, a story that explains the structure of this cost matrix. And so to do that, so what I suggest is to compute another matrix, which is the cognitive proximity matrix, which shows basically the probability that a scientist, all right, thank you. Given that a scientist has expertise in the horizontal research area, what is the probability that they also have expertise in the target research area? So basically, this matrix gives you a measure of cognitive proximity between from one research area to another. And so if scientists behave in a way that minimizes cognitive cost, what we expect is that those two matrices should be quite correlated. And so if we do that, we do find indeed that there's quite a strong correlation between those two matrices, which suggests that migration costs, as we unveil them based on empirically from scientist behavior, are anti-correlated with cognitive, distance. Proximity. All right, it's good. So now, what lessons, if any, can we draw from that? Okay, so well, again, so to join your discussion about descriptive versus normative. So descriptively, at the very least, we can say that patterns of adaptation in high-energy physics seem structured by the necessity of minimizing cognitive learning costs. And this, in turn, has the effect of maximizing the utility of the scientific capital that is distributing among scientists. So knowledge, but also maybe potentially the infrastructure that scientists have access to. And so what I think it suggests is that making the best of our prior knowledge is a key component of scientific rationality. And maybe if we want to jump into the normative realm, we could maybe say even that some level of opportunism in science is justifiable on the basis that it enhances the utility of our prior knowledge. So for instance, dark matter research, we could say is justified on the basis that it builds so well upon the scientific capital accumulated in the context of particle physics. So indeed, we observe a significant migration toward dark matter. But what's interesting is that there is a competing research program, MOND, which exchanges very little with the dark matter community. And I think there's a good reason for that, which is that unlike MOND, the dark matter approach fully exploits the particle physics knowledge it makes the best of their scientific capital, right? And so in the paradigmatic setting in the literature and theory choice, what we have is that one must choose among n theories for solving a specific problem. So for instance, here you would like to choose between dark matter and norm for solving the anomalies that they both seek to explain. But what I think is that it's at least as important from the perspective of scientists to choose among n problems, which is most relevant to address given their prior knowledge, but also in the context of particle physics, given their prior infrastructure, because there's a lot of scientific capital that is also in the form under material form. So to conclude, so I think that the first part kind of showed that philosophy of science does generate questions and does provide questions and theories that motivate quantitative approaches. But conversely, computational methods can generate insight for understanding scientific practice. So to quote Post-Maldino, when you know that a system in question involves features and constraints similar to those in models you have seen before, insight into how they operate can follow. And so in my view, optimal transport, which is an old problem introduced in a completely different context, still provides a perspective on scientific exploration under transformations of the epistemic landscape. But also, in fact, it's very interesting because it provides you with computational tools for empirical work. So it provides you with measures of change, but also potentially you can use it in a predictive manner. And so my concluding remark is that quantitative studies, they can also help generate theory. They are not merely subordinate to it. And so, thank you.
Thank you very much. Perfect time management. And so we have time for questions now. Enzo, please.
Thank you.
I'm here.
Oh, it's recording. So this was fascinating. I think I have, well, a couple of questions. One of them is more a matter of understanding. I was wondering, so when you apply the reverse version of the optimal transport framework, I suppose you are assuming that the population, the agents are optimizing something?
Yeah.
They have to be optimizers about something, right?
Yeah.
Okay, so both questions have to do with this normative, descriptive, sort of very subtle issue. So I was wondering, does this mean that there might be a way to intervene on the system to, ideally change the pattern of, shift of energies? I realize this is fairly abstract, but I was just wondering whether that is something that is compatible with the tools that you're using. The other one is, okay, you make a case that from the perspective of the agents, the kind of choices that really matter when deciding like towards which kind of issue to move may be divergent from the ones that you would see from the perspective of like theory choice or other traditional. And I wonder, is this something that we really want? I mean, what if I think that actually no? I mean, I realize again, it takes arguments. It's going to be a big challenge to make a case for that. But suppose that I have a claim that really for the benefit of the epistemic outcomes of the endeavor, I would like people to focus on that kind of alternative or that kind of classification of the field, rather than the one that is sort of driving somehow their choices. What do we do? Is this something that you can? I mean, does it have any interest for your project?
So, yeah, I think your last question really addresses the core of the issue, which is that, okay, so we observe that it does seem that this is the way people behave. I tend to draw the conclusion that there is rationale to it, which is that this is how science works, and this is why it is efficient. Now, I don't think that this is alone makes the case for that. But I would say that we can sort of draw the conclusion that scientists are reasonable in doing this and approaching things this way. For me,
I didn't mean to
Yeah.
say that they are doing something wrong as individual scientists.
yeah. But I think what I mean is that this is what makes science efficient, is this sort of underlying utilitarian sort of type of behavior, maybe, because I think to me this is a key aspect of science. This is not just an accident of it. This is because this is the only way we do science is by building upon what we've done before, and the ideas we explore are necessarily within the vicinity of the ideas that we've explored before. So to me, this is a core aspect of science, and so I don't know, maybe you know, like we would like it to be different, but it cannot be different because our creativity is limited by these sort of things. But not just our creativity. I mean, what we see in particle physics, that there are questions that are actually maybe impossible to answer because there is no technological way that we can actually gain empirical access to different domains. So what do we do now? We have built these super large experiments. We have acquired so much knowledge in whether explicit or tacit knowledge. What do we make out of it? And so that, to me, is the situation that energy physics is in. And we have to sort of navigate. So maybe you could say we just give up completely because these are sunk costs, sunk capital, and so we should. But what I think is that I think that the current approach, which is to sort of see, what we can do, given what we have, is sort of maybe like, maybe that's just the most reasonable thing. And so your first question about intervening, I was not sure I was able to answer that, but I probably did not understand what you meant. So maybe we can discuss that in more details afterwards. Sorry about that. I think that's pretty much all.
Thank you very much for the nicest presentation I have seen on field mobility, how I would call that, because that's a term I kind of came across in the 90s, and that was a term coined by Jan Vlachy in the times where Jan Vlachy was counting by hand and also counting migration from one field to another. So very nice presentation. I like it very much. I was just wondering if the motivation for the epistemic proximity, which you now kind of seem to, if this is really the dominant kind of thing. And I do remember in the 80s that the sociologists of science, and know about that much more than I do. So I know that in the context of my own PhD, I was trying to get data on field mobility. I needed that for the mathematical models, and I couldn't get really good data. But I found a lot of sociological case studies which brought together reasons for field mobility. And a lot of them I grouped them into field mobility because you are pushed out of your field, or you move because you are attracted from the other field. And some of that was epistemic, cognitive kind of, and some of them was mundane, and some of them was also no availability of places. So I think it would be interesting to dig into this. And one last question, not a really fair one, but because high energy has so long being on the top of everything, and because there is so much investment at stake in CERN, and because I have a high energy physicist at home who sighs about the crisis, so I was just wondering if you could imagine to take that to some of the experts. I mean, this is also a dangerous suggestion because knowing how expert kind of can be not on one line. So but I think doing some interviews, if you have ever a chance to do some interviews and get the perception of those, both about how they look into your representation of their field by kind of following their scholarly formal traces. Give it a try if you have time.
Yeah, so thank you very much for your questions and comments. And so regarding the first one, okay. Okay, so
Many other questions.
okay. So the first one, I say, yeah, absolutely. There are so many factors that can influence individual trajectories, which is why they are somewhat difficult to predict, at least using these methods I use, and which is why I provided the characterization of the aggregate behavior. But then, so I have this comparative analysis, which is quite limited. And for what you mentioned, I think interviews would be extremely interesting. And actually, when you compute research portfolios, you can target like interesting individuals that you can specifically reach out to for interviews because they are either emblematic of something or actually exceptions. So absolutely, yeah.
The question, what, please?
Yes, so I actually had two, but I'm gonna keep one for the later. So just I think the most philosophical and interesting one for me. So the last point you made about opportunism, right? Reminds me a lot of Nietzsche's book about scientists just doing what they want to do because it's cool and they get credit, but then this also is very good for science. So I was wondering if you think there's a way to see whether this final distribution was actually good for science, right? So is there a way to use this data that you have here and the fact that it seems that scientists did act on their personal interest to draw an argument a la Kitcher, right? So saying, oh, look, like we know that they've done their interest, but we can also show that this was actually good for high energy physics, or is there a way to do this inference or not? Maybe not, I was just curious about it. Thank you.
Yeah, no, that's again, I really think that's the core issue, which I am not able to provide an answer to that. I just think it's interesting to notice that, like scientific behavior is sort of driven by that. And then whether it's optimal it's optimal in terms of optimal transport if you look at cognitive cost. But then, again, what is best for high energy physics? I wouldn't risk myself like making a claim that, this has been best. But I really think that in high energy physics especially, it's really like, even if you look at how the experiments themselves evolve, like they build a tunnel, and then they want a larger accelerator. So what they do is that they reuse the previous tunnel if possible, or at least as an injector for the larger tunnel. And so like it's just even like this very material aspect of high energy physics have always been like to gradually reuse what you've done before, because this is so capitalistically, it's intensive, and so you have to do that. And so I just think it's interesting to notice that it is really a key component of high energy physics like development, without being able to say that whether, yeah, I mean.
Yeah, thank you. Okay, so thank you. That was an extremely interesting piece of work, and I never heard of optimal transport. So thank you for that. Immediately started thinking of how I could use it in my work.
Okay.
And actually, I have a couple of questions / comments on the technical aspects of it.
Okay.
But those are best discussed over coffee because there's little time. So we'll only ask one clarification question.
Okay.
So in the cost matrix you show on slide 21, I could see that the matrix is not symmetrical.
Yeah.
And I started thinking, okay, why? And does it make sense?
Sure. So very good question. For me, it makes a lot of sense. For me, it's a very desirable feature that it's not clear that going from one field to another, it must always be as costly as going from, the other direction, basically. So for instance, like there are very mathematical areas that are very difficult to enter maybe, but these mathematicians, they might have more abilities to enter, like, I don't know, I cannot give examples right now, but I think we have this sort of intuition that, there's some sort of asymmetry. And so inverse optimal transport is very, very recent in terms of in the literature. And so the first methods were not able to, like, they made assumptions like symmetry assumptions, which I think were not realistic. And so the nice thing about this more recent approach is that it is able to capture this fact that some directions are easier than others. So to me, it's a good, it's actually a feature, not a bug.
Thank you very much. I like very much your model. In fact, you're modelizing the kind of macroscopic behavior. And I think it works in terms of superior science. For example, I have an example which is a qualitative but fits in this logic. In the 1920s, we could predict, in fact, in the paper I did on this, debate between matrix mechanics and Schrödinger theory. Of course, both were equivalent, they say mathematically, but we could predict for sociological reason that the habitus of the people, they knew Navier-Stokes equation, they knew hydrodynamics, and they knew everything about differential equations. They knew nothing about matrix. So why should they learn matrix if it's the same theory? So in 3 years, nobody's did that. So I think it fits, and the asymmetry, I think, is good. My only technical question is, I understand quite well the fact that you get the inverse, so you get the number because it's okay. If the result they maximize, so what is it? But for how did you get? I miss how do you get the numbers for the proximity, the cognitive proximity of the field? Because that one we, for example, we can say we're going to that explain that people in mathematics go to string theory because they know the maths like. Poincaré is the genius of math. He takes the work of Lorentz and he corrects it because it's full of mistakes. So he goes up. So there is an asymmetry there. But how you get the number for this cognitive proximity?
So thank you for the wonderful example of the birth of quantum mechanics. I think it seems absolutely relevant. So now the technical question. So as part of this work, I tried to build constructs. So again, it was initially the goal was to do this comparative analysis and to look into the effect of the diversity of intellectual capital, among other things, on adaptability. And so for that, I had to sort of implement a measure of intellectual capital. And this measure is actually like a vector measure. So so if you look at the portfolio, it's basically similar to this. So basically, I construct a vector that represents how much the contribution of a specific research area in a researcher's agenda. So I take into account also, I like way more publications with fewer co-authors because they provide more information about each individual physicist's knowledge, presumably. And then what I do is to look into what is the probability that one physicist, given that he has a significant a proportion of intensity of expertise in a research area, what is the probability that he also have a significant intensity of expertise in another research area? And so this measure are based on language. So it's based on topic modeling. So what I do is I go over all the abstracts and I classify each individual keyword into research area. And basically the proportion of keywords that belong to each research area is allows to have some sort of access to the intuition is that basically linguistic behavior is a proxy for cognitive abilities. Maybe it's a strong assumption, but yeah.
Great. So thank you very much. It was really a very interesting paper. So thank you very much.